we're talking about one close to 60 and one close to 70, there's actually, it could be the first one that's close to 60 and the second one close to 70, or the first one's close to 70 and the second one's close to 60. So there's twice as many ways to get that. So what I'm saying is, I'm seeing a peak here, because this is when both come out to 60, both close to 70, and then one's close to 60 and one's close to 70. And we see this going on. Okay, so we get this with our sampling distribution. Okay, what if I take samples of size 3? What will happen? Okay, let's try that. Okay, and then we're going to ask for a histogram. Okay, and we get something a little bit stranger looking. All right, and then so I'm just going to do this a few times. This time taking samples of size 4, and just bear with me. I know this will take a little bit of time to have the computer run all of these simulations. Each time we're going to create a histogram here. So this time I'm taking samples of size 4, and just notice what happens to our histogram. As I take more and more samples, notice what happens to the shape of the histogram as well as the overall spread of the histogram. So here, that was samples of size 4. Now I've taken samples of size 5. Samples of size 6. So this is with samples of size 6. Samples of size. Yeah, the bricks felt a little funky there. Actually, let me just change down the bricks a bit. Okay, before I bore you all to death, what do we notice happening here? Yeah.
So as the sample size increases, it resembles a normal distribution curve. It comes closer toward that.
Right, and what happens to the overall spread? So this is with samples of size 8. Let's just go back to, I guess I should keep all these sample means here, rather than regenerating all of these ourselves. Let's go back to samples of size 3 and just compare what this might, how that looks. Okay. Okay. I didn't learn my lesson, so I replaced the samples of size 8. So take a look at that histogram. That was samples of size 8. This is samples of size 3. Okay. So we see that as we increase the sample size, indeed, the shape does become more normal. And what about the spread? The spread gets smaller. Okay. So, all of this to say what? Okay. Well, and that was with a bimodal population. Let's just look at our population once again. Okay, so our population is very bimodal here. Okay, what about a skewed population? What do you think would happen there? Or what if in the generation of my population, where is this? So I can even create my Okay, so let's say my population looks something like this. So I've got a skewed right, also bimodal, a weird thing going on here. Okay? What do you think would happen if I take a bunch of samples from here? Sampling distributions. Alright. So I'm just going to do a few of these, okay, just because I know it gets old quickly. But, so I run this, we're going to create a histogram based on this. Histogram of samplings. Okay, so this is with samples of size 2, and just for, I'm going to just keep increasing my sample size a little bit at a time. So now I'm taking samples of size 4. And so now we get this thing that's funny shaped, skewed, but now kind of unimodal. And even though, again, so I'm going to take samples of size 6 now, and run this, and making a histogram, we start to see this similar thing happening. So I'm going to take samples of size 10. Okay. So here we get something unimodal. I would still say it's not quite normal. Okay, we're still seeing this remnants of a right skewed, some skewness to the right. I'm going to reduce my breaks to 20, and then I'm going to just change my x limits to 55 and 60. We'll do 70, just so we get a closer view here. Maybe I'll increase my breaks again. Okay, so we're still getting something that's skewed here. So let's try taking samples of size 20. Okay. Less skew. It's a little bit more symmetric. Let's try this samples of size 30 here. Okay. And so at this point I would say, we still see this tail to be a tiny bit larger, but it looks a lot more symmetric now that I'm taking, fairly large samples of size 30. Okay, so the original population was bimodal, but also very heavily right skewed. And as I'm taking larger and larger samples, and we're looking at the sampling distribution, we see that the sampling distribution becomes unimodal and more symmetric. Okay, yes?
So if you keep increasing it, will it skew left, or is it just going to stay?
It's not going to skew left, okay? And there will probably almost always be just a tiny bit of an artifact that will make it skew right. But let's just compare this thing to the actual population itself. Oh, and I have my limits all off. Okay, so the actual population itself is very skewed to the right. Okay, very skewed to the right. But as we took larger and larger samples, we see that skewness, shrink away, and it definitely becomes unimodal. Okay, and so all of these things can be summarized with what we call the central limit theorem, which says as you take larger samples from any population, okay, and the population can be skewed, it can be bimodal, it can be unimodal. As you take larger samples from any population, if we look at the sample means and create a sampling distribution, it's going to start looking like the normal distribution. Okay. Is that okay? All right, so all of this stuff, all of this simulation on R and looking at these histograms, and I apologize for making you look at so many and waiting for all of this code to generate random samples, but I'm hoping it illustrates this idea that even if our population looks crazy like this, if I'm taking random samples and I'm looking at the mean of those samples, then the distribution of those sample means starts looking unimodal, starts looking more and more symmetric, until at some point we can say, it looks kind of like the normal distribution. Does that sound fair to say? Okay. So we'll do that. Why don't we take a little break here? Okay. We'll solidify all these